I know I've sucked the room. We can have a little preamble if you like while we're waiting for everyone else to kind of filter in. I just out of curiosity, who's kind of heard of 12-factor apps? Okay, quite a few of you. It's pretty good. And how many of you are actually applying any of those kind of principles? Okay, a few of you. And be aware this talk is pitched as basically being an introduction to 12-factor apps. So I'm not necessarily going to give you huge insights that you might already have, but feel free to take that on board. I will talk about 12-factor apps and how I see many of the factors and how I see them working in practice. But you may, if you're already doing a lot of work with it as an idea, then I don't know whether you want to think about that. We'll do some demos with .NET Core and Docker in this session. I did, if you look at the advertised version of the talk, we talked about possibly using Azure Service Fabric or Serverless, AWS Lambda, or Azure Functions. We're not going to do that in the session. It just gets a bit too deep into the weeds of technology stacks, so we're just going to use Docker to manage the containers instead. I suggest if you're really interested in looking at kind of serverless and stuff, there are a couple of other talks at the conference around serverless. There's Raj is giving one tomorrow on serverless. So if you really want to go and dig into the weeds on that, that's probably a better talk to do that on. I probably won't do that. All right, 10:20, so I'm going to start. Okay, so let's talk about 12-factor apps. What are they? What does that phrase mean? What is it about? And the idea is to run through what are they for, what actually are the 12 factors, and how might you actually apply them when you're building your own software. And we will show some simple examples in .NET Core running with Docker. My name is Ian Cooper, for those of you that don't know me. Anyway, how many of you have been to a talk I've given before? Great, I haven't put you all off yet then. So this is the kind of slide that most of you have seen before. There are only 2 points I have a call out. One is that I'm obviously old, and the second is the point on the bottom, which is just because I am standing here, there's a false notion of a power relationship which doesn't really exist. I just quite like getting up on stage and talking about stuff. It doesn't make me any smarter. And you should all feel encouraged and empowered to speak at conferences as well, right? And we often come across this mistake that people think, I don't know anything. That's probably because you know the things your peer group knows, but that may not be necessarily what everybody else knows. So do get out there, and we want to hear your voices, not just the same guys all the time. That's where I work. It's of no real interest to you whatsoever. We're a internet startup, say, cloud-based service business. Apart from the fact that I'm not a consultant, I have nothing to sell you, right? And none of the opinions given in this involve me making any money whatsoever. So you can take them with a certain amount of truth. What's our agenda? I will talk about the origins. Where does this idea of 12-factor apps come from, and why has it become important? The goals, why do people choose to follow the 12-factor constraints? What are they trying to achieve by doing that? You know, as any kind of practice, if the goals are not important to you, maybe you shouldn't follow the steps to practice. Then I divided up the 12 factors into a number of different groups. One I think of as design factors, the stuff you think about when you're designing and writing your code. One basically you need to think about really when you're building and releasing your code, and one you think about really when your code is live in production, you want to actually manage that. Okay. For clarity, I've got a couple of little icons. The top one basically says, this is about what 12 factors actually talking about. And the one below says, that's me talking about some of the concerns I have in this space. The two are not necessarily the same thing. I just want to basically get some kind of full disclosure about the two so you don't get confused. Okay. I don't think you can actually download the presentation deck because I've not actually uploaded it. So you can't do that. Hopefully you can all see everything. At the back, if you can't see anything or you can't hear anything, please just shout. It's a small enough room. We're all friends. Just tell me and I will fix your problem. But you can download the code. It's up there on GitHub. So if any of you are struggling with reading code or navigating on a big screen, please feel free to go to GitHub and get hold of that. Anyone else take a photograph? Are you there? I will put the slides up at that location, so you better get them afterwards. Mostly a talking presentation, some .NET Core and Dockers being shown. We'll show actual code, won't do any live coding, but we'll just run stuff. And as I said before, in change to published programming, we're not going to show Service Protocol Lambda. I don't get into the weeds on that. Okay, let's get into the meat of it. Where does 12-factor come from? So 12-factor apps originally came from the guys at Heroku. Heroku essentially do a platform as a service offering for deploying applications. And they originally started with Ruby, but they're now polyglot. And over time, they came to write basically a set of guidelines, which came down to 12 factors, as to what made an app successful when it was deployed into their platform as a service environment. And a guy called Adam Wiggins, who's was the co-founder effectively of Heroku. He's now an independent consultant, lives in Berlin, I think. Was, I think, one of the primary people behind driving this set of requirements. Don't worry, you don't have to read the on the right. We'll run through that. But that's basically where it comes from. And a number of people have picked up with it over time. You can see there's people have written up a book as a pivotal, have a kind of PDF ebook you can get called Beyond the 12-Factor App, etc. But a number of people have picked up on this idea of 12-factor apps as being a way that you may want to build your applications. And some people directly associate it with the term cloud native. Okay, so let's look at the goals and talk about cloud native. So what do I mean by cloud native? So cloud native apps are apps that we believe have a certain set of characteristics. The first one to probably think about is speed. Okay, so people talk about cloud native, they're often referring to this agile notion of, I want the shortest path possible between the desire to create a feature and the actual point at which I gain feedback on that feature because it's deployed live into production and running. So cloud native apps are seen as the ones that basically have a model which shortens that, probably doing continuous deployment, certainly doing potentially continuous delivery as kind of a goal. But at the same time, obviously, we want to be safe. So Cloud Native also says, well, how do we achieve that, yet maintain safety? I don't want to ship rubbish to my customers, even though I'm doing some kind of continuous deployment. I don't want them to basically say, well, it's great that you've got new features every day, but if only the app actually worked. So you need to be safe at the same time. And you need to scale. In principle, I'm building this because I'm hopeful that it's going to be very successful, potentially even virally successful. And therefore, I want to be able to scale easily. I don't want to have to kind of rewrite the whole thing when it comes to the point in time when I decide that effectively this thing's going to take off. Okay. And those kind of factors are seen as important to this idea of being kind of cloud native. So a number of ideas usually come under the bucket of cloud native. People say, if you want to build cloud native apps, these are the ideas you should bucket together. So the first one is microservices. This isn't a microservices talk. You'll probably all be grateful about that fact. You can go and see me online talking about microservices if you like, and you'll be, if you want to pursue that thought line. But obviously this idea that we don't want to create monoliths anymore, we want to slice our application up into a number of pieces. Those pieces give us some benefits. They help us scale beyond 2-pizza teams. We can have more people. But also effectively because they're smaller units, it's easier for us to release them quickly. There's lower risk involved in those releases. It's easier for any given developer to remain aware of their content. So they generally help us with a faster scale of release. And generally, microservices allow us to horizontally scale because there are large numbers of these individual parts which are kind of right-sized, and we can choose to actually scale those up. So API-based collaboration. So the other thing cloud native essentially tends to move towards is this notion that really what we care about nowadays are APIs. This notion also, of course, called API first, some people refer to it as, right? This idea that the first thing we want to think about when we're designing any kind of service is the API. And by API, we really just mean the contract that this thing is basically exposing to either other services or devices. So it could be a RESTful API, but it may also just be the contract we use basically for our messaging environment, for example. There's no real positioning about that term API. It's much more old school in that sense. But saying these services essentially communicate via APIs. Self-service agile infrastructure. What a great term that is. So the idea here is my developers are saying, oh, I talked to the product guy. The product guy's given us a great idea. We built ourselves a flashy new microservice with APIs. We want to get it live as soon as possible, right? And what we don't want is the ops guy then says, well, we could provision you a new server. We'll get basically onto the phone to the data center. That'll be about 6 weeks. And then when we've got the actual kit installed in the rack, I'll see if my team's got any availability to go and install basically an OS on it and get it all up to speed, right? That's not really going to work for us. What we really want to be able to do as developers, an idealized environment, is I just simply fill in a form and say, I want basically to have a server of this characteristic provisioned in our environment. How can I have one of those, please, right? And your infrastructure says, certainly, here you are, here is one, I spun it up for you, and you deploy to it. And this is really where a lot of these ideas like Docker, PASS, and serverless are trending towards. This idea that putting developers back in charge in a sense of being able to effectively create the infrastructure they require to service their code on demand. And it's a kind of end goal, if you like, of essentially the sort of DevOps movement where effectively teams basically are capable of deploying out to production environments. And if you do have a kind of central operations team, their role is much more in enabling the self-service agile infrastructure and providing that than it is in actually providing the individual machines that form part of that infrastructure. Okay. And finally, 12-factor. Well, I've got one more before 12-factor. So 12-factor effectively comes in because it's seen as the way to build the individual parts of your app, the microservices, if you like, such that effectively they work well in those kind of environments, particularly in self-service agile infrastructure environments. And beyond that, anti-fragile. So cloud-native apps tend to be anti-fragile. Anti-fragile is this notion that the more stress we put something under, actually the less fragile it becomes, which is a paradoxical statement. And generally what that paradoxical statement means is things like Chaos Monkey. If I essentially, in my production environment, use something like Chaos Monkey to take down servers on a regular basis, then effectively my developers will react to that approach by ensuring that they survive machine failure, and therefore my overall app's health becomes more stable. This is the notion of anti-fragility. Anti-fragile, obviously, to some extent, like I said, is much easier in self-service agile infrastructure environments, in other words, infrastructure as a service, because we effectively can provision new machines rapidly to cope with that kind of world. Okay. All right. So now you understand what cloud native is a little bit. Let's look at through what some of the goals of 12-factor apps are part of that, because I don't tend to talk about the other areas. Okay. First thing, 12-factor apps, one of their goals is basically when someone joins a team, and this happens, raise our hand, it happens at Huddle quite a lot. You join the team and you sit down to start work, and you pull the repo for your team's work, and you then want to try and build it and run it, right? And then everyone kind of goes around the rest of the room, and they start saying, well, you're going to have to install X. And then they say, oh, there's a wiki page. The wiki page tells you what you've got to install to get our app running. And suddenly you're mired in this world of complexity, and all you wanted to do was actually contribute to the team and towards their goals. And then generally, probably, you've got some hideous build script written in Rake or Saki or Fake or something else, and you're wondering what was wrong with basically just building the solution file. Why does it all suddenly got so complicated, and why do I have to understand the build script, which although it uses the same toolkit as the other teams, you've done in your own slightly idiosyncratic way because Tom or Dave thinks that's best, right? What we really want to do is remove that whole problem space. So we want to create a position where effectively a developer can sit down and pull the app and then just run it. We want to use things like Vagrant, Docker, to give us those abilities to effectively allow us to say, okay, there are scripts here which will let you just run the code. You can do Vagrant up, you can do Docker Compose up, and you can actually get running with your code immediately. Okay. Clean contract with the underlying operating system operating maximum portability between execution environments. That's fantastic, doesn't it? The key to this one really is this idea of software erosion or software rot. So Adam Wiggins-Varn talks about this quite a lot, and he talks about this, this notion that basically that software decays over time. And obviously there are two reasons for software decay. The first is the kind of death by 1,000 cuts, right? And in that problem, we're continually making changes to our software, which could be a good thing. We're expanding its capabilities, reacting to feedback from customers, but we fail to refactor. And as such, we build up technical debt until the point, effectively, that it becomes increasingly hard to maintain and look after our app. We've probably got a big ball of mud, and we've experienced software rot. That's not the object of this talk. That the problems solved there are generally you look at refactoring, and I therefore bring in TDD and everything else that goes with it. But the second problem he talks about, effectively, is the idea of I put some code on a server, and I don't change it for a year, and I come back in a year's time to figure out whether or not this thing is still running. And what problems could have occurred that mean I go there and suddenly discover the whole thing's a train wreck? And generally speaking, what we find is a lot of the problems are environmental. For example, there's a hotfix that comes out. We have to apply to all the servers because of a security threat. That gets loaded onto servers, and it has a problem interacting with our libraries. Or we have to download new versions of basically runtime. So we're dependent on like a GAC, and we essentially install new versions basically of the runtime, and our app doesn't particularly like them. It breaks them in some way, etc. We change passwords. We move a server we're dependent on like a database or another microservice, and we've hard-coded into the config file where those items live, and without doing a new deploy of our software, it's going to break. Right? I mean, how many of you think that if you left, basically, you had a server, you'd installed some code on it, and the code was running, and you basically left it for a year, but let ops maintain that server as however they need to, and never redeployed, that your code would still run? Nobody? Yeah, not many volunteers in the audience, right? So that's one other thing we're actually trying to address. It also works towards a little bit, a world in which we are increasingly possibly thinking about deploying to different environments in terms of OSs. Particularly for those of us in .NET land who may well be thinking about targeting Unix now as well as targeting Windows servers. That's quite a big change. And you want to be able to avoid constraints on given the servers that you're deploying to. Okay. Yeah, this is more of the same as the last one. Really, what it's actually saying a little bit is that we want to avoid basically relying too much on an operations team to provision servers. And so forth. We want to deploy to the kind of environments that support that, which could go up to including platform as a service or AWS Lambda or Azure Functions as models, where effectively we don't have to worry about provisioning of the containers, even the actual platform itself provisions the containers that we run in. Okay? And at certain scales of business, particularly at the beginning, it now, I think, increasingly makes sense for your initial deployments as a business to be into things like PASS and Serverless, and to leave bare metal for approaches for later in your life cycle when you need the performance, because you can't cope with basically noisy neighbors. But increasingly, it's becoming less justifiable as to why, as companies, we manage our own infrastructure. Okay. Minimize divergence between development and production, enable consistent maximum agility. This is about a number of things, but essentially, Agile used to call this inventory waste, the idea that effectively I've got code sitting essentially on my development servers that's never been deployed into production. That causes all sorts of problems, both cognitively for the developers who have a load of, well, what's living where, and also essentially for the problem effectively of managing live issues, etc. So you really want to basically have them as much as possible. But the other thing, finally, is that developers sometimes choose to use different tools in their development environment or different layouts in the development environment, topographies, than they do in production. So you have a load balancer, for example, in production, but you're not using one when you're testing locally. You decide effectively that even though you're using PostgreSQL or SQL Server in production, you're going to use SQLite on your machine or working memory on your machine. And the problem with that, of course, is that while it seems like these things probably are hidden behind some useful abstraction like an ORM or a task manager like Brighter or Celery, the reality is that it's not as hot swappable as you like to think, and you do get differences in behavior, and you want to really flush those out before you get to the production environment. because you want to be able to deploy to production without having an additional kind of like step. You want to be able to just say, well, if it works on my machine, it should work in production. Okay. And can scale up. So this idea of essentially that we would like to really think about being able to horizontally scale, to say we want to introduce new instances basically of our apps and in the event that essentially we succeed, right? So what are the obstacles to horizontal scaling? Okay. Let's talk a little bit about the factors then, and we'll run through quite what they say. Some of them are a bit strange, but we'll try and talk to what I think they mean rather than they say. Okay. And one is port binding. Expose services via port binding. What does that kind of mean? At a fundamental level, it says you should bind to a port and receive requests via that port, return responses. So it's very simple to understand this in the idea of some kind of app that's operating in a kind of microservices environment. I spin the thing up, and essentially it says I receive requests on port 80, and I basically respond effectively, right? And I'm talking HTTP. And maybe effectively I'm being really secure, and even though it's internal, it's talking on port 443 and we're doing HTTPS. But the idea essentially is that the way that I communicate with the outside world is well known, and essentially it's a port, okay? And equally, the port doesn't necessarily have to be HTTP. We can use other kinds of port. In terms of what it's trying to say as an approach, we include things like saying, I'm going to talk AMQP to you, for example. So I'm just going to listen via AMQP to a RabbitMQ broker, and I've got a subscription there, and I'm just going to receive events from you over that model. But it's really, the heart of this is saying, what I don't want to have is being hosted into some kind of application container. Now, .NET people have less of this kind of crack than Java people. Java people, are a long time heavily into the crack of app servers. But the idea is actually my app should be self-hosted. It shouldn't depend upon a given app container, because that tends to create a problem for us in terms of releasing to a given environment, and do we have that in that environment? Do we want to keep always maintaining that in that environment, right? And it's just simpler to say, well, I can self-host and spin up and just receive HTTP requests. The big one, for example, in .NET land would be IIS. IIS is effectively an application server, and certainly if you start thinking about things like I want to deploy to Docker, your question would become, well, where am I sticking IIS, right? Because if I want to be IIS hosted, or I want to use containers, well, which one of those containers holds IIS? All of them? So once you start to think about, say, for example, container models, and I find container models are one of the easy ways to think about 12-factor. In a container model like Docker, effectively, I've got a host, and that host is essentially running a number of containers. And those containers essentially are lightweight and sharing kernel operating system services. If I have something like IIS and I want to produce the equivalent of a web farm, I'm effectively installing IIS effectively across all of those containers. And that doesn't really make a lot of sense. And so in this model, it's much easier to think effectively about the model of me saying, well, I want to be hosted on port 80. Then with what I need to do is, let's get on down those. Think about basically, say, for example, having a reverse proxy or a load balancer. They live outside, essentially, of my application and talk to it over the port that it binds. So this is very common in environments like, in programming languages like Python or Ruby, effectively, et cetera, where you tend to basically spin up something that effectively says, so you spin up your Python web server and with Unicorn or whatever, and you say, okay, right, that's going to serve over port 80, and I'm then going to use Nginx or something to actually act as a web server sitting outside my app. And in .NET Core, this is certainly the same model, right? Effectively, you can do IIS integration, but the preferred model, particularly if you want to deploy to Unix as well as towards Windows, where there is no IIS on Unix, you're definitely looking much more at a model where you say, I want to basically self-host, talk to port 80, and then if you need to, you can load balance me and everything else, basically using something like Nginx or HA proxy, right? This is really the heart of this one, is saying, please don't use app servers. Okay. Backing services. Treat backing services as attached resources. Okay, the first question is, what is a backing service? A backing service is something like a database, message-oriented middleware, or even potentially another service that we talk to, another app that we talk to get our work done, right? And a 12-factor app says that we treat these basically as attached resources. What do we mean by that? Well, the idea effectively is they should be hot swappable. So in theory, what we're going to say is effectively, well, I may be talking to the database here, effectively, but essentially it might move tomorrow and move here. And then today it might be hosted on bare metal, and tomorrow it might be in RDS. And I don't really care. All I care about is that I have some means to communicate with, like a connection string. That's all really this says. And I want to better attach and deploy things at will. It's a fairly straightforward requirement. I don't think nowadays many of us build applications that don't work that way. One of the things that I would recommend in terms of the ethos of this, though, is I would always recommend thinking in terms of building your app as a ports and adapters architecture. But the reason I like ports and adapters is because they make this idea very explicit of the separation between your code, which essentially you care about running in your domain model in the center, and the adapters on the outside, which talk to external concerns, right? With a port layer in between managing that process. So you separate your model from all the I/O and ports mediate. So basically you have primary adapters, those are the inputs, and they're essentially the ports that you're effectively listening on, that you're exposing. And you can have different adapters. So basically your tests can drive your ports, but also essentially you can use something like, a web API for your HTTP adapter or Flask, whatever your language's preference is, right? And the advantage basically of this model is because you're managing that via a port, you can swap these. So if, for example, you suddenly discovered that the .NET Framework 4.5.2 was no longer the target of choice and you wanted to port your code over .NET Core, but you needed to use the new version of Web API that came with that, you'd find that if you wrote your code such that most of it lived in the domain and the ports, with a thin adapter layer over the outside, that kind of swap model becomes much easier. Secondary adapters are outputs. Those are things I'm talking to, effectively like the database, etc. Now, the output-input thing is a little bit off because obviously I get information back from my database as well. But you want to think basically of this thing on the right-hand side, of things that I talk to in order to fill that original request. Okay. And the secondary adapters are really what I think of as the backing services. We talked earlier on about this notion of bind to a port. And I think basically this other notion of actually saying make sure effectively you treat resources as backing services leads you naturally towards a hexagonal architecture, where essentially you're clearly separating yourself from the means effectively by which you communicate with the outside world. Okay. Strongly consider using the service location. Okay. We'll talk a little bit why you might be using environment variables, but any kind of configuration in an environment variable or a file may well require a restart for your application. But also the other problem is that they become difficult to manage. If I have two machines talking to each other, then yes, probably I might be able to feel comfortable about going and altering the config file on one when I move the other one to another location. But obviously there'd be downtime during that process when effectively I had to go in and do the manual edit or redeploy effectively my config files out to the new location and get things working again. And so, but even with two machines, you might think, well, it'd be better effectively if I could just find where this machine is by asking it. But once you get into the business of hundreds of machines, it's unrealistic to think that you might actually by hand say, I've moved this basically, this app that I'm talking to, this other microservice, I've now deployed it out to a new set of servers, and so you need to change the IP addresses and all these servers that talked to it originally by hand, or you need to redeploy all those servers to make that work. So you're going to have to use some kind of service discovery. What do we mean by service discovery in this context? We mean some kind of distributed key value store, console, zookeeper, something like that, which you can essentially query to ask it for the locations of services, and essentially some mechanism by where you automatically register new services when they come online. So you can do sweet things with things like console and registrator and Nginx, for example. You can say, get Nginx, get console, get registrator, whenever basically, and put it in Docker, and you can say, whenever basically a new Docker container comes in with basically, it's a web app, you have a template which rewrites the config file for Nginx and will therefore add that machine into basically a group which effectively Nginx then load balances across. And you can do most of that with stuff that's available on Docker for you to pull down today without even writing a line of code. And that kind of model which says, what I want to be able to do is deploy very rapidly and ensure that other services are aware of my existence and can route to me, is kind of a prerequisite to any kind of real self-service infrastructure. Okay. Processes and concurrency. Okay. Execute the app as one or more stateless processes. Okay. The first key takeaway on this stuff is statelessness, right? This is probably, one that most of us now get. But essentially, your server process should always be stateless. What you don't want is to force yourself into the world of sticky sessions. You do not want to be in a place where when user A comes in and talks to you and gets routed to a given server, they have to keep hitting that server because you have some state on that server. Usually what happens is someone's written to a cache which is local to that the memory in that given server, and they've cached some information like a shopping cart or something like that. And now we have to basically pull requests to exactly that server in order basically to keep it working. So Huddle had this at one point. We had a problem at one point whereby when you did file uploads, rather than writing to a shared file system, shared storage, they effectively wrote to the local file system on the server you're uploading to, which meant you had to be sticky for the length of your request. And that's obviously a problem because it doesn't allow you to balance traffic correctly, and it means if that machine goes down, then the user's request or workload is lost. So we never do sticky sessions if we essentially want to be able to scale. Okay. So you tend to be what's called state aware instead. In other words, we recognize that you may have state, but you should store it in some kind of backing store, which effectively you can reach as a shared resource. So that could be SQL Server or MongoDB or whatever your database of choice is, but it could also be something like Redis, right? Effectively, what you really want to do is a kind of almost a more in-memory workload for a cache. Okay. You can use memory of file system process for a brief single transaction cache. And what we mean by that is some cases you do have a workload that during the lifetime of the request requires you to write something away, where like streaming something to disk, etc., because you intend to complete during the operation that process. But otherwise, don't do it. The other thing to think about is if you start to think about basically environments like serverless environments, right? You have no guarantee in a serverless environment, if you're deploying, say, AWS Lambda, that the container which is spun up to, everyone understands probably that maybe that in serverless, effectively, I write something essentially around a function, and that function essentially I can hook into, respond to something like a request, like an HTTP request. Eventually I bind it to a port, and then what happens is Amazon spins up a container, and that container is used to service your request. Now, it may reuse the container between requests. It's indeterminate from your perspective. It's Amazon deciding whether or not effectively it can optimize that. And that gives you, if you have any startup time on your container, obviously the advantage of that is you don't pay that cost every time. You could be unwise and decide essentially, therefore, that effectively I'm going to use the local file system in my serverless environment to cache some information. But that's going to be useless to you because you've got no real guarantee that the next time you receive the request, you won't actually have a fresh container and you can't access the contents basically of the file system. So you have to use shared storage like S3, effectively, etc., instead in that particular, or EFS in that particular instance, because it's the only way you can guarantee that basically you'll survive between requests. So you do have some local resources, you can use them, but assume that their lifetime is only the request. Scale out by the process model, okay. Prefer to scale out with new instances of the process. What 12 Factor is definitely not saying is that in programming runtimes that basically support concurrency well, you shouldn't use multiple threads, okay. So if you're in the JVM or the CLR, you should certainly consider using multiple threads in your workload. And if you're in Python and you're doing I/O, you should certainly think about potentially using threads, right? Just don't use it if you're CPU bound. But the scale out of your application should not depend on vertically scaling the instance that your code is running on so as to effectively make more CPU power available to the machine, because vertical scaling is problematic. You should instead opt for horizontal scaling. In other words, introduce new instances of your process. So we all know how to do this essentially because we've done it for ages in the web by building, for example, web farms, where effectively we've said, well, okay, I'll just introduce new copies of everything in order to have more capacity, basically, to meet the demand that I'm facing. But generally speaking, it's easier to use processes to do this model, right? And particularly when you get into the kind of post-container world, or the post-basically virtualized environment world, even if you're running VMware, you're effectively, you're optimizing the bare metal by running certain virtual machines on it and trying to sandbox stuff. In a world like Docker, effectively, what you're trying to do is sandbox your given application inside a container, run it on a shared resource like a host, but you're effectively more able to use multiple CPUs on the actual hardware more effectively by using processes, because you get process isolation, and if you get failure of that individual process, essentially in the sandbox environment, you don't impact everything next to you, then you are effectively if you try and scale up by using multiple threads. So, one of the early mistakes we've made was to have servers which were running multiple apps, because essentially the server we'd bought at Rackspace or whatever had large numbers of CPUs, and to maximize the use of that server if it's running a single instance of the OS, you'd effectively have apps that effectively scaled up heavily by using lots of threads, because that was a fairly straightforward model. Where once you get into more of a virtualized environment, it's much easier to start thinking about scaling using sandbox processes. Essentially won't impact other items on the server, because if you get a runaway process, we've had that. We had a runaway process that was dealing with video conversion. It can easily take out the entire memory space on the server, crash everything else. And in a moment of foolishness, at one point, we were actually running video conversion on the same box as RabbitMQ. And someone's video, when being converted, took out basically our message broker. You don't want to do that. That would be my advice. So cleanly separate stuff is basically one advantage, basically, of moving to a process-based scaling model, right? And running sandboxes. You separate processes of different workloads. I'll talk about this a little bit more when we show some code. So generally speaking, a good rule of thumb for something like an HTTP workload is that you should respond within about 250 milliseconds to be scalable. If you can't respond within that time frame, then the best thing to do is to kind of hand off that work to basically a work or task queue and get it to process that. So a work or task queue is just using something like a message-oriented middleware or Redis to maintain a queue of work, and then a worker process then reads off that queue of work and actually then performs the action in the background, right? And separate that enables you to scale. And one of the reasons it's useful to separate those two into different processes is because essentially you may find that the bottleneck is not your web server, which is able to effectively now to meet the throughput of requests and hand them back out easily. The bottleneck is actually the processing of the work, basically by your worker process. And in order to avoid becoming too eventually consistent, then what you may want to do is introduce additional workers to make sure you're reading through that queue as fast as possible. So by having those as two separate running processes, your background worker process and effectively your web process, you're able to scale more effectively. By contrast, if what you did was in your web front end, use span off a thread to go and deal with some long-running piece of work, you cannot scale that separately, because essentially you're now scaling the whole web server in order basically to meet effectively that demand. Okay? And you're also basically using resources which should go towards servicing web requests, servicing back-end processes, and you're defeating your ability to schedule by moving effectively the work and the worker processes and the web processes to different locations, different servers. Okay. As all processes are share nothing, in other words, they're stateless, then it's fairly straightforward for us to basically increase capacity under a model where effectively we have additional processes by simply introducing new instances of the process. So in, say, a Docker environment, you'd effectively spin up a new container. The other kind of admonition here is to avoid doing things like using demonization of the process, but just rely on a system's process manager. So in Unix, you're talking about initd or systemd or upstart, that kind of thing. In Windows, what this is really trying to ask us to avoid doing is making everything a Windows service. So, I've drunk the top shelf crack, or smoked the top shelf crack, I guess we'd say, and have lots of lovely Windows services that basically run on Windows environments, managing basically worker processes. But it's not portable across execution environments. As soon as I do that, I get into a world where that code now can't run on a Unix server. Whereas if I use Task Scheduler and I'm just running a console application, then that's actually portable across execution environments because I can use an equivalent on Unix to then run basically that console application, right? So think about effectively how you are managed in the operating environment. You don't really want to basically plug yourself too deeply into that operating system by doing things like writing your own demonization services. That's fairly obvious. You need to cache expensive items. So we're saying basically that you can't effectively use process memory to cache stuff between requests or the file system. Use backing services such as Redis basically to do this work instead. Okay. And shared storage. Again. Disposability, maximize robustness for startup and grades for shutdown, right? And this is one's pretty much about the fact that if I want to basically scale by deploying new instances of my application, then obviously I want them to start up quickly. There's no point in effectively me being able to say, oh, I can deploy a new instance of my application in about an hour. That's really not going to help me. And effectively, there's no point if my app says, well, I'm going to do a whole lot of work before I actually answer requests, and it takes me about 10 minutes to actually get running before I can answer requests, right? You don't want to be in that position. You want to be in a position where effectively I can bring up new capacity to meet throughput rapidly. Oops, that seems to be jumping around. I've not got my animation right there. Stop gracefully. When we say stop gracefully, what we mean is that when we actually are terminated, we should terminate in a reasonable time frame. We want to consider how we're processing any running work. Okay. So, say the model at Nginx or Brighter, the OSS library I work on for task processes, we say we'll finish the current running request for you. So if we have requests in flight, they'll finish them before effectively they shut down. Now, that can cause you some issues in some cases where effectively your preference would not be to do complete running work because that running work takes a long time. So, for example, if you're doing video conversion, it takes a long time to basically shut the service down. In that case, essentially, what you really want to do is more have a model where you would knack back to a queue, for example, to say, okay, I'm not going to complete this work or give a response to the user indicating failure and then stop. In that case, some of those cases, you may need to consider whether you're within a transaction, effectively, you can effectively roll back when you stop, or essentially you're idempotent and you don't care if a request has been partially complete and you'll actually then just service it again. It is an easier cognitive model to stop gracefully by actually finishing work that's currently in process. But if your shutdown times are too long, you may have to go into other areas. What we're looking at here, try and get is elastic scaling, right? So we're looking to make our apps elastic and that we can effectively deploy new instances, have those instances automatically register with some kind of service discovery tool, have our load balancers begin directing traffic to them, or have them start basically consuming traffic off queues, and have them start up and do that quickly because they're meeting demand, or be able to shut them down quickly because we no longer want to pay for them because we're no longer actually using them, or we want to basically move workload between various environments to schedule properly. Okay. All right, we'll show you some code. Because you're probably all bored with me talking about design factors. Are there any particular questions at that point? No? Good? Okay. So we have some code which we've been writing, various teams have been writing a huddle kind of example of, looking at how we might look at doing using .NET Core. And so we took as a project for a number of teams. So there are other examples other than just the team I work with. Took it as a project basically doing to do backend. So I don't know if you know, but to do backend essentially is a set of tests out there which let you essentially implement an API server, and it's people who have basically shown implementations meeting that particular requirement in a number of given frameworks. Okay, so we took that specification to use. We added into, we wanted to do some asynchronous workloads, so we added a bulk add in so that we could basically demonstrate handing that work off to a separate worker process to process over a queue. It originally was inspired by a to-do project which basically deals with front-end frameworks, for example, Angular, React, and shows how they all build basically a task management light app, right? And there are a set of, you probably can't see that slide, so I'll ignore that one, tests that you can run to get that working. So the first thing I'll do is I will attempt to show you this working, and then we will, okay. Then we'll have a look at the code. How am I doing for time? Okay, am I due to finish at 11:20, I guess, or yeah. So we're running basically Docker, and we're using Docker Compose, and we basically have a number of containers out there. There's a Rabbit one, so basically we have a Rabbit broker, and we've basically got a web, essentially, container, which essentially is hosting our API and receiving requests. We have a worker. We have a work that basically is reading work off the Rabbit queues and processing in the background, and we have Nginx acting as a reverse proxy. Okay. And over here, and I will go back so you can see better, I have basically the tests. So this is basically the to-do backend tests. I'm running them locally. You can run them straight offline, but I just wanted to make sure it's going to run in a conference talk. And essentially that is the address effectively of my app, which is basically sitting at port 8080, and that is the Docker machine address, effectively. And when I run those tests, you'll see essentially that it's going to run through and say I meet all the specified requirements of the to-do app. All this code is available on GitHub, so you can go and get it down and run it yourself. And the acid test, what we're saying is true, should be that you should be able to pull it down, run the Docker Compose file, and actually get the code working. I hope. And then you can see we're proving that point about being able to get hold of your code base and just run it. Just to show you there's a whole lot of HTTP requests going on in the back end. There's doing some gets, some posts, some updates, that kind of thing, etc. Right. And we can also offload a back-end workload. So this is going to do a post request to basically, there's only one item, it's to a bulk endpoint. In theory, we could have hundreds of items. And when we execute that one in Fiddler, this is not part of the original test, we'll get a 202 response back saying, accepted the work. It's an act back to us to say, you can move on with your lives, I've got the work. And that gets processed essentially by our worker process. So if I look at actually I've probably got in the history, the logs, basically the worker process, you can see essentially at the bottom, hopefully, that what it's done is the whole big spray of JSON is essentially where I'm receiving a message off the wire. I'm just basically debugging what I'm receiving. And then I'm building a pipeline, found a pipeline basically for that particular command. And then essentially I'm logging that I'm actually calling the pipeline. And at a certain point, I acknowledge the message back to Rabbit MQ, so I've completed the work. Okay. I think also the other thing in there that might be interesting to show you, you'll find in the log history, is this, yeah. I started the service up a little while before the talk, just to avoid timing issues. When this service first started up, it basically got a broker unreachable exception. So one of the things is that with Docker effectively Compose, I was starting up a whole set of boxes together, and by the time the worker starts asking Rabbit basically to make a connection, Rabbit's actually not ready. It's not spun up effectively on its box. So one of the things you do have to cope with in these kind of scenarios is you have to make sure whatever you're using is resilient to those kind of timing errors, right? Where you have to say, well, I'm trying to talk this out of the box, and I can't right now. So potentially my first option is to retry, and then things like circuit breakers, where effectively you say I can't talk to it for a while. So Brighter, which is the .NET open source library I work on, one of the things here is effectively although it's basically got an exception talking to the broker, it has a retry policy, and it will effectively come back at some point and connect. And you can see down here, whoops, I've scrolled too far. Here, if I can highlight it. This area down here, you can see essentially we're saying we're now successfully talking to the broker on that particular line. So you have to be aware in these kind of environments that you can get things like timing issues. Your code has to be able to cope with that. You don't really want to basically be forced to kind of like start one box, wait, start another box, wait, right? Essentially, your script may create those timing issues, and you want to basically move through that. Okay. In terms of some code, let's look at this. What I may show you actually somewhere here. So this was all kind of started up with a Docker Compose file. So that's just essentially saying I've got a number of Docker files and I want you to basically run them all. For simplicity, I'm actually showing you the app rather than an image. So there's the 2 API, which is basically our first one. It's essentially starting up. Set some environment variables, just bear that in mind, come back to that, creates the web box. Says it depends on Rabbit, and then there's effectively also, excuse my scrolling, which is a bit my trackpad is a little bit oversensitive for this font size. Hang on, 2 hands. Okay, there's a web and a worker. Effectively, this is the back-end process. And then there's Rabbit. We'll come back and look at exactly kind of some of those Docker files, things a bit more in a second. But things to note. So if we go and look at basically to do API here, let me try. I think I may have it open. Program. Okay, you can see here effectively, this is basically the web API. You can see here effectively that we are using Kestrel, we're not using IIS integration, and we're just listening on a port. Okay, so that whole notion of saying bind to ports and don't be inside an application container, that's what we're doing here effectively. We're making sure that works. How that works, this is pretty standard in a sense. You've got a controller here listening to the message. What we do is we use a couple of libraries that we work on internally. They're open sourced out there. So this get one, for example, there's essentially a CQRS framework, brighter and darker. Darker is the top one, basically. That's essentially doing the query effectively on a get. And we've also effectively down here for, say, an add. Here you've got brighter, which essentially is a command handler. So I basically issue a command and a handler will pick it up. You can... All this code, by the way, Control tab and Alt tab, is available online, so you can go to the code and peruse it in your heart's content. This is essentially the command handler that receives that command, add a to-do. I'm just using Entity Framework here to effectively do our work. Everything in .NET Core, by the way, everything is basically async, right? You want to be async because essentially it's got the libov engine library underneath, and effectively you're basically doing a reactor pattern, basically eventing for throughput. Right, what's the other thing? The other thing you may want to see here is that effectively we have essentially a Nginx proxy config, and we use that in the Docker Compose file basically to direct traffic to the web. Now, the only other thing worth pointing to here, if I can scroll this in a way that doesn't kill me during this talk. Right, so you'll see in here we've basically got to do API, to do app, and to do core. So to do core effectively is our domain model, our handlers, commands, that kind of thing. So these essentially host those. And to do app is our worker runtime that reads from a queue, and that just uses brighter. I won't go into the whole depth of what's going on, but essentially you can see here what we're doing is simply saying we're going to basically create a connection to a given broker, and we're going to, which is essentially a routing table, and we start a dispatcher which will receive messages effectively from the broker. And it's just a console application. So essentially we just run a console application and we use something like scheduler or even just the container itself to keep that up and running. Okay, I think that's what I wanted to talk about for this one. I've got another note here. Anything I didn't talk about quickly? Yeah, both the worker and web processor run separate processes. Okay. Go back to the slide deck. How am I doing for time? 8 minutes. Right. Let's keep moving. Codebase. One codebase traction and vision control many deploys. Essentially what this is just saying really is that your app should live in a repo in source control. One app is one repo, multiple repos are a distributed system. Now, so what they mean by this is effectively that you shouldn't have a repo which contains your entire system. That's kind of pointless. You want an app per repo. I think this has been kind of mooted a little bit by the notion of microservices, where effectively nowadays we're talking about effectively a business capability. And it makes sense logically, obviously, any team's business capability would lead in their own repository. There is some dispute when you talk about this one over the situation we have, I've just shown you, we have effectively to do API and to do app. And they're both effectively in the same code base, right? And so is that a violation? And the guys at Pivotal would say, yes, essentially every process should live in essentially its own app. I say no. To me, effectively, the solution boundary is the CI boundary. It says essentially I want to pull that and build it together. And that, to me, is basically, if it's a CI boundary, it's a bounded context boundary, and therefore, essentially, it is the whole of your business capability, your microservice. So if essentially you can have multiple processes inside a microservice, where Udi Dahan would call them autonomous components, if you accept that model, then I think it's acceptable to have essentially multiple processes inside the same code base. Your app is a microservice, essentially, under this model. Okay, so you're applying 12-factor on top of microservices. And I think in that case it's okay, because you are building it as one. It is one CI boundary. And as a corollary later, we'll talk about basically management processes, but generally they're construction of 12 factors to basically put those with the rest of your code. So I think it makes sense, and quite often you're sharing the domain model. So I would say choose one repo per microservice stroke app. Shared code management, dependency manager, not shared source and wrapper. In other words, use NuGet or use pip or whatever you want to. Deploys running instance app using the same repo. So basically, you can have one repo, many deploys. Okay. Note from me, I would say always ship trunk. Okay. I would really avoid feature branching. The thing is, essentially, as soon as you get into the world of feature branches, you're no longer doing continuous integration. People are living now on long-lived branches, and you're no longer integrating with them regularly. You always cope with a distributed version control system with branches, because essentially every developer has a branch. And the advice we usually give to people is integrate multiple times during the day to avoid issues with your colleagues, basically, and having great merge problems. So generally speaking, you really do want to have this model where effectively you say, we just have one code line and everyone integrates with it. The only exception would be if you're doing some kind of big refactoring, but usually the whole team would then be effectively on that branch. You're simply saying, I need to preserve the integrity of my current code line, which represents what's in master, because effectively I might need to do some kind of hotfix release. This, bear in mind, is predicated on the idea that we don't want too much of a distance between production and development, and therefore I want to release on a regular basis, and therefore the time window in which basically my stream effectively in development and production are out is very short. And you can always tag what is current production in case you need it. Unlike client apps, where some of these practices about feature branches come from, branching really supports this model of effectively deploying out to multiple locations outside your control, where you may have multiple versions of your software running at any one time. That's really what branching is for. It's not for saying, I'm going to do my development in an isolated sandbox from you. And in the web environment or services, we usually should only have one version live at any one given time. And use feature switches. Okay. Right. I don't know whether this one will actually finish in the time frame, so let me just, this little thing here says to me, we'll do an escape, but it says to me, go into the background and try pulling down the code. I was going to show you essentially, if I could, building it. We may run out of time simply on the basis that I don't know how good the network is going to be for us, how kind it is rather, but let's try cloning the future stack. Oh, that's not bad. All right, well, we'll try building it then. So what we're going to do is a Docker file in there, essentially, and we're going to build it. And it's going to go away and build it. So I've just put down a fresh version of my app to try and demonstrate that we can basically put down a fresh version and build it. What I should do, actually, over here, though, is if I can actually get something I can read. Hello, hang on. I'm going to reduce the font on this slightly, gentlemen, just so I can read it. Where's my cursor? Stop that one. All right, and we will try building that one when we get, okay. So we're not going to watch it build because it takes longer than we probably got. Hopefully it'll build nicely in the background while we're doing stuff. Okay. Especially declare and isolate all dependencies. So what we don't want to do basically is have a model where effectively we depend upon a shared runtime installed on an OS which we cohabit with other applications. So we need isolation, effectively, from any kind of shared runtime. We don't want to basically have multiple apps installed under Windows running from the GAC. The reason is because, essentially, if we have that shared dependency, if someone else needs it updated, it could break our app. The notion of software erosion we were talking about earlier. So we want to make sure that we control within our app all the dependencies. So all we need is basically the language and the runtime installed, and all of the libraries we require to have our app should be explicitly declared, and we will then pull them in. So Project JSON is great for this. CS Proj, who knows? You can, if you're in Python, you can kind of do pip freeze to requirements text and pip install requirements text. It's a sort of standard pattern for doing that, and you manage virtual M's in Python as well. Containers really help here because essentially you can run in a container and be the only person using effectively the libraries installed in that environment. So within inside a container, you could get away with using something like a GAC because you're the only person actually ever deploying into that container. I assume that's pretty obvious, by the way. Only one app per container, right? And effectively, etc. Our model should be kind of cloned down from the repo, restore our dependencies, build effectively our software, and then run it. Okay. In a containerized environment, basically, you can use essentially the tooling. In non-containerized environments, obviously, you may want to use something like Chef, Puppet, or Ansible to basically put your machine in the correct state. Right. Pull, restore, and build. Let's see where we are on that one. Actually, I may go on and come back to it because it's probably still building. Store config in the environment. Okay. Configuration is what, in this sense, is use a particular phrase. We mean anything that varies between environments. We do not mean, for example, your routing table for your web framework. We do not mean, essentially, the message queue subscriptions for your worker process. What we mean, essentially, is something that varies between environments. So, for example, a connection string to the database, timeouts, number of processes you're running, perhaps, the elements, essentially, which do change for each environment which you deploy to. So the events between production and staging and deployment, passwords, for example. And that's what configuration is, right? A 12-factor app says, essentially, only code should ever be checked into your repository, not configuration. Okay? As much as possible, try and put many things that you may think of today as configuration, which don't vary between environments, put them in code. But don't put anything into basic repository. Particularly bear in mind, for example, that you don't want to put anything into a public repo that effectively contains things like your AWS, for example, passwords. But the rule of thumb people have here is, if I checked in, put my repo live on GitHub rather than some sort of private GitHub or enterprise GitHub, would there be any secrets in that config file that I wouldn't want anyone to see? If there are, they shouldn't be in your repo. They should be somewhere else, right? And generally, the technology basically people tend to use is to store it in environment variables. Very easy with containers. You saw effectively when I looked at Docker Compose file, I was basically setting up the environment variables for that particular container when I was running it. Very easy to vary that between environments, basically, when you're ops doing deployment. In certain environments, for example, serverless, effectively, environment variables are probably about the only thing you have access to. You don't really have config files on disk that you can use to control basically how processing. So you have to use an environment variable model. But the 12-factor app model says we're trying to make ourselves suitable for those environments, so you should use config. What you don't want to have is some hideous build script that goes away and says, I've got a templated config file which I merge with secret hidden lists of values for given environments that I've produced to. Because your release artifact should be immutable. Once I've built it, that's what ships. And the only thing I need to vary for environment, basically, is environment variables, right? And you can, locally, you can either put things in your IDE will support you setting environment variables, or you can essentially use something like basically a PowerShell script to set your environment variables, or a bash script, okay, for you on your app. .NET has a quite nice feature in that if you're using its .NET Core's configure class, you can actually order where it looks at places. So you could, for local environments, if you wanted to, use a local config with an environment variable as basically override on it. So you could say, well, actually, my developers, when they pull it down, I don't want them to have to set environment variables. So what I'm going to do is put in my local config those values so they can pull it down and get running with whatever I assume are my defaults for stuff installed on a local machine. And then if that works, then essentially when it deploys to production environments, it will always assume the environment variables replace those local values. You could do that, but generally speaking, I think it's quite a lot nowadays easier quite often to get your developers running by using like a Docker file that has the environment variables in it for them. Okay. Build, release, and run. Strictly separate build and release and run stages. This is fairly straightforward. Essentially, the idea effectively is that I want to release immutable artifacts. I don't want there to be changes to code at runtime. So realistically, what I want to do is only release publish artifacts that essentially you then effectively can run, but you cannot basically subvert my process by changing the code live, then checking it back into my source code repository, right? I understand in 2017 this may seem strange, but when the Heroku guys wrote this, they were writing it for an audience of PHP hackers who would quite often modify their code live on the server, right? We're all wiser than that, I'm sure. So release is a combination of build and config. Run stage actually happen in a given environment, right? Okay. Dev prod parity, keep development and production as similar as possible. So things we're worried about, time gap. Right, so we don't often always think about some of these other factors. The time gap, what do we mean by that? We mean that we're concerned that essentially that effectively we have inventory waste. We have things that have not been deployed to production because our developers haven't got, are too far out of line because we have a too long a deployment process. We build stuff and then it's like 6 weeks before it gets deployed. That's not agile because you're not getting fast feedback. So we should have a low time gap. Development and production should look very similar because the time gap is low. Personnel gap, we don't want effectively to separate between operations team members effectively and development team members. We don't want basically a lack of knowledge about our production environment as opposed to our development environment. And a tools gap. We don't want to use different things in different environments. So what it might seem straightforward, for example, using something like Brighter effectively to use RabbitMQ locally, then deploy to Amazon using SQS and SNS. The problem with that is they have different characteristics, and you're going to meet different problems in those environments. So you want to try and, as much as possible, deploy to what the environment looks like. And things like Docker really help you with this, because they let you essentially create something that looks like your production environment. Manage logs. Create logs as event streams. So this one is quite straightforward. Basically, the idea is to log to standard out. Okay? If you log to standard out, then, or in AWS Lambda, for example, you can use print statements. Generally speaking, what you want to do is have a stream that your app produces, and then you use something like ELK to manage basically your logs. Particularly in microservices environments, you now have many apps. If you log to the local file system, there are a number of problems. One is you may not have a local file system. Number two, it could be ephemeral, particularly, for example, in a serverless environment. It's going to go away between invokes of basically your container. And even in a Docker environment, effectively, your containers will vanish when you finish running them. So any logs you've logged locally will be lost. You could try to log into a shared directory, but you might as well be smarter and actually just log to standard out and get something like ELK to pick it up effectively and collate all your logs for you where you can search them and deal with them. And then use things like correlation IDs to map between them, right? Because you now have logs from many sources. And so you don't want to log all those sources into different shared folders. You just want to collate them in one database. Okay. I can see if we can show you that other one working. And then we're almost done. So I'm probably overrunning slightly. I am. All right, let me just show you this. I'm not in the right directory. That won't work. Okay, we'll skip showing you that. We showed you the code running earlier. I'd have to basically shell into the right directory. I forgot to do that and do a build. And it takes quite a while, basically, over this shitty network connection. But you can download it yourself after the talk and go and run Docker Compose and build it. And you should see it just build straight out of the whack and you can run it, which is kind of the goal, right, effectively. And it's actually a better goal if you do it at off-site than here. Okay. Last pieces. I'm sorry, apologize for overrunning. Dependence. Supposed to we've done that one. Why have we gone backwards? Release run. Propriety. Manage admin. Okay. Admin processes. Essentially, this is just saying, whoops. We may have little processes like migration scripts or tooling to do operational support, almost done. And those processes, effectively, when we use them, should be located along with our app in the same repo. Otherwise, what happens is developers forget about them. They make changes to schema and that kind of thing, et cetera, and they forget to update the tools that work with it. So always collate your tools. Generally, you want to use command line infrastructure to do it. And if you're working things like .NET, you can use things like .NET CLI, effectively, to basically integrate neatly with that. Okay. Summary. So, 12 factors. 1 code-based tracks and revision control many deploys. Okay. Explicitly declare and isolate your dependencies. Store config in your environment. Treat backing services as attached resources. Strictly separate build and run stages. And execute the app as one or more stateless processes. Okay. Export services via port bindings. That's what we talked about, basically avoid application service containers. Scale it by the process model, i.e. horizontal scaling. Fast startup and graceful shutdown. In other words, be prepared for basically elastic scaling. Keep development stage and production as similar as possible. Don't forget, it's not just about tooling, it's also about time and personnel. Treat logs as event streams, just shove them into Elk. And admin management tasks as one-off processes, effectively. Make sure that your supporting code is kept with your main code. All right. Thanks so much. I apologize for overrunning. Please do, it would be an interesting exercise for me, download the Future Stack code, right, and then try and run it locally. If it doesn't work, obviously I need to fix things, but the goal should be to just run that and run the Docker Compose file and get it up and running, provided you have Docker obviously running on your machine. Thanks very much. Please vote, especially if it's green, because then they know that you love me. If you give me yellow, they will wonder what happened. And if you give me red, that's okay. Thanks very much. And I'm about the conference. If you want to talk to me, come and grab me over a coffee or food. I'm happy to chat about stuff. Thanks very much.